Hello, welcome back. Our next speaker is Daniel Aronsson. Now, Daniel is a senior application engineer at MathWorks. He specializes in signal processing and communications system design. He has several years of experience in these fields, and he also works regularly with computer vision and FPGA system implementation. He holds a Ph.D. degree in wireless communications from Uppsala University and in Sweden, specifically on MIMO channel prediction. So, raising the abstraction level, let's put our virtual hands together for Daniel Aronsson.
So thank you for that introduction and welcome to this presentation on raising the abstraction level. Here we will talk about how you can use a dynamically typed high-level language, MATLAB, as a kind of an extra compiler on top of your C compiler to raise the abstraction level to quickly get from a few simple lines in MATLAB all the way to readable C or C++ or CUDA code. All this will be done completely automatically by using tools that we will look at today. But before we get there, let's spend a few minutes on what MATLAB is for those of you who are not too familiar with it. So what is MATLAB? So as most of you are familiar with, I think MATLAB is a complete programming language together with an IDE. It's a powerful software environment that is really built for engineers to quickly get started and get doing what they need to do. It's easy to learn and to code and scale up to bigger projects, and it's built in a rigorous way so that everything is thoroughly tested and fully documented. You add functionality to MATLAB by adding toolboxes. So if you work on a specific field, you can simply add the toolbox that is associated with that field, and that will allow you to build up the total functionality at hand. What we try to do when we build MATLAB and build these toolboxes is to have interactive apps to go with the toolboxes that will allow you to quickly get started and doing things by point and click. And once you have everything set up the way you want it, you can then automatically generate MATLAB code out of that. To do what you've just done by point and click, you can then do programmatically. So that will allow you to quickly get started with your programming projects. But then what we're going to talk about today is that once you have that MATLAB code written, how do you get from there to C or C++ code? And there we have something called MATLAB Coder that will allow you to take a MATLAB function and really translate that into C code. And if you think about it, it's quite a difference between MATLAB code and C code, because MATLAB is a dynamically typed language, right? So everything is all the data types, all the variables have data types and sizes that are really decided runtime. So you can change the data type and you can change the size as you go. In C that is not so. So in C everything needs to be statically typed. So going from MATLAB to C is quite an undertaking, and that is where MATLAB Coder will help you. So there are a few different use cases. So in going from MATLAB to C, some people want to just generate C code to hand that off to software engineers. Other people want to sit on the same, sit on both chairs, so to speak, so that they both are coding in MATLAB and C, and they want to integrate their generated code directly into their bigger C projects. Some people also want to prototype their MATLAB algorithms as standalone executables, and that is also something that you can do with this tool. And lastly, some people want to stay in MATLAB, but they want to use automatic C code generation to speed up their algorithms. What we're going to focus on today is really the first one, or the first two ones, where you quickly go from MATLAB to something that is readable in C, and you can hand that off to software engineers. So that is what we're going to talk about today. You may ask yourself, what is it that you, what kind of algorithms is it that you can actually translate to C code? And a few years back, the support was actually quite limited. But as the years went by and we expanded of the capabilities of MATLAB Coder, we now see that actually most things that you can do in MATLAB will actually translate automatically to C via MATLAB Coder. So there are a few functionalities that are still not supported, but they are getting very scarce. As I mentioned before, you add upon the functionality that you have at hand by adding toolboxes to MATLAB. And the same goes for automatic C code generation. So most toolboxes that we have functionalities that support automatic C code generation. So let's say you work on I don't know, automated driving, and you write your algorithm for tracking the cars around you. Then you can quickly prototype that in MATLAB and automatically generate C out of that. If on the other hand you work on, I don't know, 5G, and then you add 5G toolbox, and by so you get functionality for let's say a polar decoder that you're working on. You can then take the polar decoder that comes with 5G toolbox and automatically generate C out of that. So by adding toolboxes, you actually have a lot of functionality at your fingertips. So most people that I talk to when it comes to automatic C code generation are people that are experts on digital signal processing. But they may not be as versed with writing C code. So what they want to do is to take their DSP expertise and add MATLAB Coder to sort of automatically bring in that knowledge of C to produce a DSP algorithm written in C. Now I expect that many of you on the call today are actually C programmers. On the other hand, you may not have all the expertise in DSP that some projects may ask for. So you can actually do the opposite thing here, to use your C expertise and use MATLAB Coder to bring in that DSP expertise. So as we just saw on the slide before, let's say you have a filter, a signal filter, or a signal decimator or something like that, or an FFT. And you need to produce an algorithm written in C that uses that kind of maths. Then you can use MATLAB plus the right toolbox to actually automatically generate a function for that digital signal processing and bring that into your handwritten C project. So it's really a way also to use MATLAB's functionality for all the digital signal processing that are in there, and use MATLAB Coder to bring in that as automatically generated C code. So today I'm going to use a very simple example here to show the capabilities of automatic C code generation. I'm going to use a filter as an example. So what does a filter do? Well, you have some input coming into a filter that illustrated by x0, x1, x2 and so on, and out comes y0, y1 and y2 and so on. And inside that filter you have a few coefficients. In this case I've chosen to have 5 coefficients, and really what comes out on the filter, on the output of the filter, is a weighted sum of the inputs, right? So the fifth output of the filter will be a weighted sum of the first 5 inputs to the filter, as you see here. And the next sample that comes out will be a weighted sum of the inputs number 2 through number 6, and so on and so forth. So that's how a digital filter works. And you can more compactly write that on vector form. So you say vector y equals some matrix A times these filter coefficients, where A is then comprised of the inputs, as you see here. So I'm basically building up the inputs coming in for the different 5 time shifts here. And so in this case, we're going to ask ourselves, what are the coefficients of this filter? So we imagine a filter but the coefficients are unknown. Application here could be in wireless communications. So you have a wireless communications channel, a fading channel, and you don't know the coefficients of that channel. Or it could be maybe power amplifier, and you need to model that power amplifier, and you need to figure out how to model that. May not be a linear model in that case, but I mean, more or less, you'd have this kind of problem there. So finding unknown filter coefficients is a fairly general problem, you could say. So this is what we want to do here. So how do we go about doing that? So we take that vector formulation that we see there, we write it even more compactly, so we say vector y equals matrix A times a vector h. We want to find that vector h, and in MATLAB that's trivial because you use the backslash operator. So we say h hat. By hat here I mean that it's an estimate of h. So h hat equals a backslash y, and that's it. That's all you have to do to find an estimate of these unknown filter coefficients h. So that's what we're going to look at here. So with that, let me go to MATLAB. So I'm going to bring in my MATLAB window here, so that you can see that, hopefully. So what we're going to do here is to start and say edit function m. I'm going to write my my function there to find these filter coefficients. So I'm going to say h hat equals some function. I'm going to just call it fcn here. It's a bad coding practice, I know. And we're going to take the input to the filter and the output coming out of the filter, and from there we're going to find the unknown coefficients that we just saw. And as you saw, the simple way of doing that is just to take some matrix A backslash y, and then of course we need to form that matrix A. So I'm going to say here x. The input x from the fifth element all the way to the end, and then the fourth element all the way to end except 1, the third element all the way to end except 2. Notice here that I'm actually hard coding the length of the filter. I mean, more ideally I might want to do something that could take any length of filter, but here I'm going to keep it simple and hard code the length of the filter 5. So that's my function, and then to go with that I will probably want to write some test script. So I'm going to create a test script there that I'm calling the function name _tb for test bench. So that's something that's fairly common, and in this case I'm going to test it. So I'm going to say, okay, we use some random input to the filter, so 10,000 random values, and here I'm going to make up some filter coefficients, and these are really the coefficients that I want to recover, and I'm going to say just 5 values here. Could be anything, but I'm just going to pick 0, 1, 0.8, 0.6, and so on and so forth and so on. So that's my filter coefficients. What comes out? Well, that's just, so y, that's the output of the filter, and that is going to be the filter coefficients. 1 for the denominator, this is an FIR filter, and this is what comes out. Okay, so that's the reality, and from the reality I'm going to then test my function on the inputs and outputs there, and to see if I can recover that h I had there. So in this case I'm going to do this. They will probably come out in different orders, but that doesn't really matter. So if I run this now, I did some error here, so let's see, what did I do? 5 and 4 and 3 and 2 and, okay, I made a typo there in the, and it should be and -1, -2, -3 and -4. This is what happens when you do things live. And then I made some other error. Let's see, what was that? Well, actually y should be probably the 5th up to the end, because I have a tail there that won't fit, so I need to cut away the 4 first elements here. So let's see if that is right. And now we call that, and actually let me go back and remove the semicolons. That means that if I remove the semicolons, I'm going to suppress the, if I have semicolons, I'm going to suppress the output. So now I get the output. And here you see that my correct input is there. That's these values, and what I get out are these values. They come out in different orders because the way I set it up, but that doesn't really matter. So you see the algorithm is now working here. So from there, the question is now, so now I have an algorithm that I have tested in MATLAB, and it's written in MATLAB and tested in MATLAB. And how would I go about to actually generate code for this? And what we're going to do now is to open up an app that is called, so if I go to the Apps tab in MATLAB here, I will find an app that is called, so down here I have code generation, and it's called MATLAB Coder. So I'm going to open up that app. So as I mentioned in the beginning, we try to do it so that for the different toolboxes that we have, we try to have apps that will allow you to quickly get started with these tools. So the first thing it's going to ask me for is the function name. So I'm going to then point to that function, and then I'm going to go to next, and then the only thing actually that MATLAB Coder needs to understand when you generate code from MATLAB to C is what are the input data types and the input sizes, because from there it's going to be able to figure out all the sizes and types of all the internals in the function. And that is essential because in C you need to define those data types and sizes once and for all when you set up the function. So that is something that cannot be decided runtime as it's done in MATLAB, but it needs to be figured out from the beginning. But the only thing you need to provide is actually the types and sizes of the inputs, not all the internals like the matrix A in this case, because MATLAB Coder will be able to figure that out itself. So in this case, I could actually use the test script to get MATLAB Coder to figure out these types and sizes from the test script directly. Here I'm going to actually do it manually. So I'm going to say that I put in doubles here, and I'm putting in a vector, a 10,000 by 1 vector of type double. The same for y, so I'm going to 10,000. I hope this is not too small so that you can see it. So these are the input data types. Now I can click next. I will skip that one actually and go directly to code generation. So here I can actually choose what kind of output I want. So if you remember in the beginning, some people want to use this for speed up, and they can produce what's called a MEX function. Some people want to produce a static library or dynamic library. You can do it here as well. In this case, I'm going to generate standalone readable just C code. So let's click on generate. I'm going to make this a little bit bigger. Takes a while for MATLAB Coder to go through all the transformations that are required going from MATLAB to C. So it takes a while to build that that C code, but it's worth the while. So what you will see here is that over here I have this source code. Actually, let me open up the report instead. So what you will see here is that this is the original function that I had. I can actually hover over the function and you can see the data types that MATLAB Coder has deduced. So you can see that this is actually a size 9996 by 5 matrix of type double. So you can hover over here and see that it makes sure that it got everything correctly. But everything is of course automatically done here. We can also trace the code, so I can click on trace MATLAB code, and here you will see the MATLAB code, and you will see the generate C code here. So if I click on a line here, I can actually take that line first, that puts together. You will see how that is reflected here, so you can see in the generated code how it loops over and sets together this matrix A, fills in all the values for the matrix A, and down here you will be able to see how the backslash operator, just a one-liner in MATLAB, is actually reflected in several, actually hundreds of lines in this case. But what you will see, so you can use that traceability to better understand what happens here, but what you will see, so let me turn that off and just go to the C code, is that these two lines in MATLAB has been generated, in this case, about 340 lines of C code. That is to be expected. To do this least squared solution the way the backslash operator is doing it is actually quite complicated. You need to do a lots of exceptions and things like that, and that needs to go into the code here. So you see how our two lines was expanded into 340 lines. But something that is also evident here is that this may or may not be what you're looking for. So in this case, everything is implemented in a way, you can say, rather naively, in for loops. So it's by default generating ANSI C code that will compile on any platform. And we'll look at later how you can change the configuration and get something that is maybe a little bit more efficient, depending on what platform you have. But for now, just notice how easy it was to get from MATLAB to a few lines in MATLAB to many lines in C. So I'm going to close down that report. Something that you can do now, if I mentioned in the beginning, we have these apps that allow you to quickly get started, as we've seen here. Something else that something that we try to do with these apps is to, once you've done what you're looking for, you can actually generate MATLAB code out of that to automate it in the future. So in this case, I'm going to go to the menu here and say convert to script, and that will create a script that does this automatically does this directly from the command line, and we'll look at that. So I now automatically generated that script. So if we look at the script, you will see that I got a few commands here that will do this from the command line. We'll look at that in a few short minutes, but before we leave the app, I'm going to show you one more thing, and that is I'm going to go back all the way from the beginning, because something that we didn't look at here is that in the generated code, everything is statically typed here. So you see that all the data types here are actually, if I go down to my function prototype here, so it's further down somewhere here, you see that all the data types here are 10,000 long. So these are my input vectors, 10,000 long. And you will also see in the generated code, all my internals here are actually static sizes. This is likely what you want, because that means that you don't need to do any memory allocation via the operating system. Everything is statically typed, and you can compile this onto an embedded system even without that doesn't even run an operating system. But so in many cases, this is exactly what you want. You want to be able to have a function in MATLAB that is very generic, and you can call it with any types. And then once you generate code from there, then you, in the code generation process, you do what we just did now. You say, generate code for this for specific sizes and get specialized code out of that. But in some cases, you may also want to produce more generic code. So I'm going to go back to the beginning, where we specify the sizes here. And I'm going to do something else. So you see I specify the size 10,000. I'm going to specify the sizes as colon 10,000, which means to up to 10,000. So that will allow my code to accept data sizes that are up to a certain size, but they can be smaller. I'm going to specify that and go back and see what happens then. So we go back, we are now reconfigured the code generation process to accept those dynamic data sizes, and I'm rebuilding the code. And what we'll see now, if I go down a little bit here, is that the function prototype that before took the static 10,000 x and y, now they have these other types that we define actually in files down here. So you see this called EMX API. So we define automatically, we generate out an API that will accept dynamic data sizes. So this will allow you to, I won't go down into any detail here, but this will allow you to, when you call this function, to specify data sizes that are dynamic. What is the drawback here? Well, if we go down in the code, you will see that it now uses function calls that look like this. So you have something called EMX, ensure capacity. So that means that every now and then in the code, the operating system needs to make sure that or the generated code needs to make sure that the right amount of memory is allocated. So it needs to call out to these kind of functions. And if I were to go into that function, maybe I can go to the report here instead. So if I were to go into that, click into that function, you will see, so now it jumped to this emxutil.c that we generate together with the main function. You will see that it down here, it's going to use things like dynamic memory allocation, like calloc, so to call out the operating system to allocate memory. And this may or may not be what you want. So if you need that kind of versatility in your generated code, then you can easily do that by just reconfigure the code like this. But you need to be aware of that you also get code that is more inefficient than if you would use static allocation. But with MATLAB Coder, it's just a matter of a small reconfiguration, as we just saw now. You don't need to change anything in the original MATLAB code. Okay, so with that, let me leave this app and go back to MATLAB and go back to this script that we just saw. So what I'm going to do now is to note that what the way you call this from the command line is actually via, I'm going to clean up a little bit here. It's actually via, let's see, I think I took something away there. No, sorry, it's down here actually. So you call a function called cogen. That's how you generate code from the command line. So what we're going to do here is to, I'm going to tidy up a little bit, so remove that. So what we're going to do here is to call cogen, and I'm going to say the function is the function that we want to generate code for, and then I need to specify the arguments. In this case, I can just say the arguments is of the type x and y that we already have in the workspace here. And then I'm going to use a configuration object, and that is simply say encoder config lib, and this is essentially going to create for me a configuration object that generates standalone C code. So that's how easy it is to generate code from the command line. So I'm going to add a few extra ones. I'm going to say don't compile, only generate the code, and also launch the report once you're done. So I'm going to save that and run that. And this is going to do what we just saw. It's going to generate code for this, for statically typed static data sizes, and I'm going to get the report out. Okay, so that is that's how easy it is to do from the command line. So now we saw how I could go back and reconfigure, change the configuration to get dynamic memory allocation and so on. What I want to do here is to reconfigure the code in a different way. So when we do it like this, we will get a standard NCC code out that will compile on anything. But what we could also do is to use this configuration object. So if I were to, I'm going to clear everything in the command window, and I'm going to maximize it so we only see that, and look at this configuration object. You see that there are a lot of different settings that you can change here. So you can go in here and change everything that we can change in the app. You can change programmatically here. But one of the things that we can do here is to go in and say change something called a code replacement library. And I'm going to change that to I think it's called that. Yeah. Okay. So in this here I'm going to say actually generate C code, but generate it for a specific platform like this. So if I rerun this now, so I'm going to run this section that only runs lines 5 through 8. Takes a while, so you see down here it says busy, so it's now generating code. But now if we go into the generated code again, we shift down a little bit here, we're going to see that I get function calls that look a little bit strange like this. It's called mm256 store UPD and so on and so forth. It's underscore mm256. And these are vector instructions that are specific to this Intel platform. So what happened here is that by just changing one configuration in this configuration object, I actually got what's called SIMD instructions, so vector instructions that are specific for this platform. So just by changing this, I got code that is essentially different from the ANSI code that I got up here, but will be much more efficient in that it's using vector instructions that only works for this processor when it carries out this this code, this least squares solution. There's one more thing before we move on that I would like to show you. It's quite a big thing, and I wish we had more time to go into detail here, but I'm going to remove this, and then I'm going to change this configuration to instead say coder.gpu config. I think the C should be capital here, and I'm going to call that instead. And this is actually going to call out to a tool that is not called MATLAB Coder but GPU Coder. And GPU Coder generates CUDA code that will run on NVIDIA GPUs. So what happens here is that the generated code now is actually called FCN, not .c but CU, which stands for CUDA. It looks like a little bit. It looks like C for the most part, but it's actually going to use. So if we look here, here's the function. So you see it looks like the function prototype looks the same as before with the static sizes, the 10,000 and 10,000 vectors coming in. But what's going to happen here is that it's going to allocate memory on the GPU, and then it's going to copy over the data from the CPU to the GPU and call out to these different kernels, and the kernels will execute massively parallel on the GPU. And once that is done, it's going to copy everything back to the CPU, and you get the results. So what happens here is that it generates this CUDA code, it generates these GPU kernels that you see here. That will be, you can go into the code here and see what they look like, and they will execute massively parallel on the different threads on the GPU. And everything is again, notice how little I changed. Actually, I just changed that line to get now the same code that small code again, but now get that in the form of GPU code. And if you remember the ANSI code that we had in the beginning, that was 340 lines, and now we're up to 760 lines just for the CUDA code, just to do this on the GPU. So it's a very small changes will allow you to do vastly different things and quickly test a lot of different solutions. And programming in GPU is not an easy undertaking, and it's really a problem of minimizing the transfer back and forth between the CPU and the GPU, and that is what one of the things that GPU coder is trying to minimize there. A lot of different more things that we could talk about here. Deep learning is a big topic that is very commonly common target for GPU coder and GPUs. So you can train a deep neural network, use that in MATLAB, and then generate CUDA code that will execute on the GPU for that. So the big topic that I now just spent 5 minutes on. But what I want to focus on here is how little I did to get 3 different versions of the same functionality in vastly different forms. So that was the short demo in MATLAB. Now I'm going to go back to my slides. So what we saw here is that with one design, while with 2 lines in MATLAB, we get multiple configurations. So ANSI code that will compile on anything by default, and then you can change this code replacement library setting and get platform specific code. In this case we got this vector SIMD instructions, and also if you have a GPU coder, you can get CUDA code out. I mean, depending on the problem, it may not be that not all problems are a good fit for GPUs, but if they contain a lot of parallelism and linear algebra, then, or deep learning, then it's a good fit for GPUs, and then GPU coder is an interesting tool to take a look at. That's basically it, what I wanted to show you today. But before we finish, let me just bring a few extra topics into the picture here that we haven't dealt with. So one is that you may want to bring your own handwritten C code into the picture. So here I have a handwritten piece of code written in C on the left side, and on the right side you can see how you can integrate that into your MATLAB code. So you use this command called coder.ceval, and you point to the name of that function. And in this case, what you need to watch out for is that in this case we had a pointer. The first argument is a pointer, and then you use this coder.ref. The other one is just a regular value, and then you just insert that like that. But if it's a pointer, you use this coder.ref. Pointers don't exist otherwise in MATLAB. So, and if you were to generate C code out of this, you would see that it would just, this line, call out to your handwritten C code. So it's very easy to incorporate your own handwritten C code into your automatically generated C code. And the last thing I would like to mention is that once you have your generated C code, and it may then contain snippets of handwritten C code as well, you may want to check your code for runtime errors to mathematically prove that it's sound code. And we have a tool called Polyspace that will allow you to do that. So here I have a small piece of C code, and it may not be obvious whether this code is safe or not. And what Polyspace will allow you to do is to prove different things. So for example, it could say that it uses different colors. So for example, it could say that at that line it green lights that. So writing to that pointer like you do there, that's actually safe. It's sound. And you can see in the code that it may not be obvious if you're not very good at C that this is sound, but you can actually, the tool will prove that this is something that you can do. But then there's a problem here, because it can mathematically prove that this will be out of bounds. So that is a big red no-no there. It can also prove dead code. So in this case, we'll see that this code will never be reached, and it reached, and it will mark that as gray. So that is dead code that you may not want there. Can also be things that are unproven. So in this case, we don't know what the value of I there, so the tool cannot prove whether this is green or red. And the last thing that it can do is that even if a line is programmatically sound, it may violate some coding standards. So in this case, it may violate the MISRA C coding standard. So it will warn for that as well if you need to comply with a certain coding habit there. So that is Polyspace. And to finish off, I just want to summarize what we've done today. So first of all, we looked at MATLAB Coder and GPU Coder and how you can produce readable C, C++, and CUDA code from MATLAB. We used apps to quickly get started, so that's usually the first starting point. Start the app, play around with it, try to do whatever it is that you want to do, and then automatically generate MATLAB code out of that from that app to automate the process in the future. And then we looked at the different configurations that allow you to switch between dynamic and static memory allocation there. And also incorporation of handwritten C code by using the coder.ceval command. And lastly, Polyspace is a tool that uses formal methods to prove the absence of critical runtime errors. So you can use that. Whether that is not in any way tied to MATLAB Coder and GPU Coder, it's something that you can use of any C code, even if everything is handwritten. Maybe especially if it's handwritten, actually. So that is what I wanted to show you today. So with that, thank you for attending. I hope you found it useful, and have a nice day.
Daniel, thank you so much for your presentation. That was perfect. We're going to take a short break now, but don't go away. Stay with us for more presentations at Code Dive.